You know, we see them everywhere, these skeletons of steel and wood clinging to the sides of buildings. Scaffolds are such a common part of our cityscapes that we barely even notice them anymore. But behind every single one, there's a set of rules, a code, that's designed to keep workers safe, sometimes dozens of feet up in the air. So today, we're going to pull back the curtain on those unseen rules and break down the code that keeps people safe.
So let me ask you a question. When you picture a construction site in your head, what do you think is the most dangerous part? Is it the heavy machinery? The heights? All the power tools? Well, you could make a pretty strong argument that it's the one thing that's meant to disappear, the scaffold. Yeah, the fact that it's temporary is exactly what makes it so risky. I mean, unlike the final building, it's not designed to last forever, which means every single connection, every choice of material, and every single inspection is absolutely critically important.
So, in this explainer, we're going to break down the official safety code. We'll kick things off with why scaffolds fail by looking at the materials themselves. Then, we'll dive into the anatomy of a safe structure, zoom in on ropes, which can be a real weak link, and we'll finish up with probably the most important habit of all, the daily safety check.
Okay, first up, choosing your materials. This right here is the foundation of scaffold safety. Long before anyone even thinks about climbing up, the choices made right on the ground are what determine how safe it's going to be for everyone up in the air. This is your first line of defense. What's really fascinating is just how specific the safety code gets. It's not just about using a rope, it's about using the right one. The standard is explicit. It recommends manila rope because of its incredible tensile strength. A good quality sizzle rope, on the other hand, is only about 2/3 as strong. And that is a huge difference when we're talking about something holding up a platform, not to mention people.
And to put a number on it, a single pure manila fiber has a tensile strength of about 230 megapascals. Now, to give you an idea of what that actually means, that's roughly the same strength as some types of aluminum. It's incredible. That durability is the benchmark. It's the gold standard the whole code is built on, and it just reminds us that safety is really rooted in hard physics.
But, even the toughest material has its kryptonite. There are these silent destroyers that can just eat away at a rope's integrity from the inside out. A rope left out in the rain, it gets saturated and weak. One that's been dragged across the ground, it picks up all this abrasive grit that works its way inside, literally cutting fibers within. Heck, even just storing it the wrong way can cause damage you might not see at first glance.
All right, so let's see how all these materials actually come together. It's not enough just to have strong parts. You have to assemble them into a system that's stable. A scaffold is a system where every single piece has a job. Let's take a look at the anatomy of that system. So this diagram here shows a pretty typical independent scaffold. Now, it might look like a complex web of tubes and couplers, but it's actually a very logical system. We're going to break down 4 of the most critical parts you see here so you can really understand how they all lock together to create a safe platform.
Okay, we'll start with the ledger. This is a horizontal tube, and it runs parallel to the building. Its main gig is to connect the vertical poles, which are called standards, and that gives the scaffold its length and its stability. Think of it like the spine of the whole structure. Then you've got the transom. These are the shorter horizontal pieces that run at a right angle to the building, connecting the inner and outer ledgers, and their job is absolutely crucial. They directly support the boards of the working platform. They are literally bearing the load of the workers, their tools, their materials, everything.
And this is what makes the scaffold more than just a big box. The brace. This is the diagonal tube. Without it, the structure is just a bunch of rectangles that could easily wobble and just collapse. The brace creates triangles, and triangles are incredibly strong. It's what gives the entire scaffold its rigidity and stops that dangerous swaying motion.
And what's holding it all up? The base plate. It might seem like a small part, but it's literally the scaffold's foundation. Each vertical standard sits right on top of one of these. Its whole purpose is to spread out the immense weight of the entire structure over a wider area so the poles don't sink into the ground, especially if that ground is a little soft.
So let's circle back to one of those materials we talked about earlier, ropes. In a whole system of rigid steel, it's pretty easy to see a flexible rope as the weakest link, right? So how does the safety code make sure this potential point of failure actually becomes a reliable lifeline? The code does not mince words. This is a direct quote, and it's a pretty stark warning. Something as simple as rain can rapidly degrade a rope if it's not taken care of properly. It really drives home the point that maintenance isn't some optional thing. It's a core safety requirement. And check this out. Here's another one of those incredibly specific rules that prevents damage. Any pulley a rope runs over has to have a diameter at least 30 times the diameter of the rope itself. Why? Well, it's simple physics. A small pulley forces the rope into a really sharp, tight bend, and that just strains and breaks the internal fibers. A bigger pulley gives it a much gentler curve, which preserves the rope's strength.
Okay, so we've got the right materials and we've got the right design. But what's the final piece of the puzzle? Well, it's the human element. A scaffold doesn't just stay safe on its own. Safety is an action. It's a continuous process of inspection and just being diligent.
But how do you actually tell if a rope is compromised? I mean, how can you know if it's on the verge of failing just by looking at it? Well, the code gives us a really clear, practical method for that.
Here it is, the 3-step rope inspection. And this is straight from the standard. First, you do an external check. You're looking for obvious stuff: abrasions, cuts, broken fibers. Second, the internal check. You actually open up the strands a little bit to look inside. Healthy inner fibers should look bright and clean, not dull or discolored. And third, the tenacity test. You take a little piece of yarn from the rope, and if you can snap it easily with your hands, the entire rope is compromised and has to be taken out of service immediately.
The code also covers special gear, like the boatswain's chair. And notice the emphasis here. The ropes have to be secured to a fixed structure, the hauling line has to be reachable, and most importantly, using a safety belt is mandatory. There's no negotiation on that. It's that final layer of protection for a worker who's in a uniquely vulnerable spot.
So, let's bring it all home. What are the big takeaways here? First, safety starts with quality materials. No cutting corners. Second, you have to respect the design. Every single part, from the base plate to the brace, has a critical job to do. Third, inspect your equipment relentlessly, especially those lifelines like ropes. And finally, always remember the silent threats. Moisture, chemicals, abrasion, they can cause a catastrophic failure if they're ignored. And all of this leaves us with one final thought. After seeing all these rules and specifications, you really have to ask yourself, is a safety code just a list of boxes you have to tick off? Or is it something more? Is it a mindset, a culture of diligence and of looking out for one another that turns a temporary structure into a safe place to work?
When you think about the dangers on a construction site, what comes to mind? Probably the big stuff, right? Heavy machinery, live wires, maybe even deep trenches. But what if I told you that one of the biggest, most frequent killers is something most people use every single day without even thinking twice about it? Let's get into it. So what is it? Well, it's not the crane. It's definitely not the grinder. Nope. It's the simple, humble ladder. It's kind of shocking, really, when you think about it. So many preventable falls, serious injuries, and even deaths, they all start with this one piece of equipment. And it usually comes down to a basic misunderstanding of the forces involved. And look, these causes, they're pulled straight from the safety standards own forward, and they tell a really important story. See, we're not talking about freak accidents here, not at all. These are predictable, preventable failures. Things like climbing up or down the wrong way, forgetting to secure the ladder at the top and the bottom, or just using a ladder that's already got a crack in it. You know, simple mistakes that can have absolutely devastating consequences. But here's the good news. All that risk, all that chaos, it doesn't have to be the reality. This isn't about luck or just being careful. It's about engineering. And the best part is, there is a clear, well-documented blueprint out there that's designed to replace all that guesswork with solid certainty and to stop these accidents from ever happening in the first place. And here it is. This is the blueprint I'm talking about. Indian Standard 3696 Part 2. Now, I know what you might be thinking, another dry, dusty document. But no, this is so much more than that. It's a comprehensive code of safety. You should really think of it as, like, all the collected wisdom, all the engineering principles, all bundled together to guide you on how to pick, build, and use every single ladder, every single time. So that's what we're going to do today. We are going to deconstruct this vital standard. We're going to treat it just like that engineering blueprint, really get to grips with the basic framework that holds the whole thing together. Because honestly, knowing why the rules are there, that's the absolute key to making them work in the real world. Okay, so every good blueprint has to start with a clear definition, right? We all need to be on the same page. The standard defines a ladder very specifically to create a common language. So it's not just that thing you climb. Nope. It's a very specific piece of equipment with side rails and cross pieces. And believe me, that level of precision, it's the bedrock of everything we're about to talk about. All right, so the very first thing the code does is break down ladders into different types. And the reason for this is super simple. Using a stepladder when you really need an extension ladder, That's like trying to use a screwdriver as a hammer. It's just the wrong tool for the job. And that mistake, right there, is often the very first domino to fall in a serious accident.
So the standard basically puts all ladders into these three main families. Now, each one has a totally specific purpose, a different design behind it, and of course, its own set of rules for how to build it and use it safely. Let's take a quick look at each one.
First up, we have built-up ladders. The easiest way to think about these is as semi-permanent fixtures. You know, the kind you'd see in a really big construction project. They're literally built right there on the job for one specific need, fastened securely to the building, and they're not meant to be moved around. Their whole purpose is to give stable, fixed access for as long as that job takes. Then you've got rope ladders. As you can probably guess, their big thing is flexibility. This makes them really useful for getting into confined spaces, like inside a tank or down a deep shaft. But, and this is a big but, because they aren't rigid, their safety depends 100% on being hung from a super strong, totally secure anchor point at the top. No exceptions. But the category that you and I are probably most familiar with, the one we see and use all the time, and frankly, the one responsible for most accidents, that's portable ladders. These are the everyday workhorses, right? And because they're so common, the standard gets even more detailed about them. So inside this big portable category, the standard breaks it down even more. We get specific types like stock ladders, extension ladders, sectional ones, even step ladders and trestle ladders. And the key thing to remember is that each one of these has its own specific design and, most importantly, its own set of safety rules. And this is a perfect example of just how detailed the code gets. Let's just take the two most common lean-to type ladders. A stock ladder, that's just a single piece, and it can't be longer than 10 meters. But an extension ladder, well, that has those sliding sections with locking guides, and it can go all the way up to 18 meters. The code has totally different rules for them because their mechanics and the ways they can fail are completely different. So what about that classic A-frame ladder we all have in our garage? The standard calls these step ladders self-supporting. Now here's the absolutely crucial part. They must, and I mean must, have an automatic locking device or spreader. You know that little bar or hinge that clicks into place? That's not just a suggestion. It is a mandatory engineered safety feature designed to stop the legs from splaying out and collapsing right from under you. Okay, so the standard has laid out all the different types of ladders. But what actually gives a ladder its strength? I mean, you can't just slap one together with any old scrap wood or metal, right? Of course not. To guarantee its structural integrity, the code gets incredibly specific about the materials you're allowed to use. This right here really shows you how safety is a whole system of interlocking standards. It's not just use steel, it's use steel that conforms to IS 1977, because that standard guarantees its strength and how much it can bend before it fails. The aluminum has to meet IS 617, which makes sure it's the right alloy and it won't get brittle over time. Even the rope for a rope ladder has its own standard and has to be at least 25 millimeters thick. You see, there is absolutely zero room for guesswork here. And really, it all boils down to this one single, powerful statement from Clause 6.1.1. All of these rules, all the talk about types, materials, dimensions, it all serves this one ultimate goal, to make absolutely sure that every ladder can safely carry the load it was designed for without failing. Okay, so let's recap. We've laid the groundwork. We've seen how the standard sorts ladders into different types and how it demands specific, high-quality materials to build them. So now, you basically have the blueprint for what a safe ladder is. But here's the thing. That's only half the story. Knowing the blueprint is one thing, right? But what about knowing the exact angle to place that ladder? Or the critical load test it has to pass before anyone ever climbs it? What about the daily checks you absolutely have to perform? That's where knowledge turns into action. And that's what actually saves lives. And we're going to cover all of that, all the hands-on rules for construction, for testing, inspection, and how you use it day to day in part 2 of our deep dive into IS 3696. So, to make sure you do not miss that essential next chapter, go ahead and subscribe to ISO Automation Lab. We break down the standards that are designed to keep you safe on the job, one clause at a time.